This week, Ro and I are going to be talking about the radiometric dating of rocks and minerals. And in the process, we'll talk about the mineral zircon. We'll point out, for example, that zircon incorporates uranium as it grows, and therefore it can be dated. But there's a lot of minerals that can be dated. Zircon is special, and the reason it's special is because it's basically revolutionized our understanding of early Earth, and that's what I want to talk about today. In order to talk about that, let's pose the question, where does the first zircon come from? And to do that, let's move to the Bushveld complex in South Africa. We're going to talk about the Bushveld because, first of all, that's where I work, and so I have a ready slide. But the Bushveld complex is a large body of gabbroic rocks. It formed by partial melting of the mantle, and that magma buoyantly rose and then was trapped in the shallow crust, and there it solidified. If one takes these rocks and crushes them and then separates the minerals by density, one finds that the Bushveld rocks contain zircon. Note the scale here. These zircon crystals are on the order of a few hundred microns across. They're not abundant, but they're widespread in Bushveld rocks. So this process of partial melting of the mantle and the rise of these sort of primordial magmas, whether they rise to the crust and erupt as basaltic lavas, or perhaps they're trapped below the surface to crystallize like the Bushveld complex, that's where we imagine the first zircons to form in the early Earth. So now what happens to those zircons once they're formed? Well, in this photograph, you can see down here, there's a stream, right? And that stream is, of course, eroding the Bushveld as it's eroding all the rocks on the surface. The minerals in these rocks, as they tumble down the stream, are becoming abraded, and the relatively soft minerals, such as felspar and pyroxene and affable and so on, they're abraded to relatively fine particles. They're washed into rivers and then into the ocean. Harder particles, such as those of the mineral quartz, which has a hardness of 5.5, don't get abraded so much. In the case of quartz, they end up concentrated in beaches. And then there's zircon. Zircon has a hardness of 7.5, and so it's probably the hardest mineral in the Bushveld complex, and one of the hardest minerals in any surface rocks. So there's nothing to abrade it. So the point is that these zircons are basically maintain their size and to some extent their shape as they're washed down rivers and into the ocean, and they end up there in sediments. So this is what happens then. These sediments accumulate in sedimentary basins in the ocean. The sedimentary basins, as they fill with sediments, they deepen. Thus, as you go deeper in this sedimentary pile, the temperatures and the pressures increase. Initially, the sediments, as they're buried, turn to rock. They're lithified, in other words. As burial continues and the temperatures and the pressures increase, there's a whole sequence of mineral and mineral fluid, mineral reactions that progressively change those metamorphic rocks to higher and higher grade rocks. Some of these sedimentary sequences during mountain building episodes can be thrust underneath others, and they're subjected to even higher temperatures and pressures. Now, how do we know all this? Well, the way we know all this is because in mountain building episodes, those sequences of deep-seated metamorphic rocks that can make up the roots of mountain belts are exhumed by the erosion of the overlying material, and we see them at the surface. And here's an example in the Himalayas where you see very, very steep sloped mountains eroding, producing these enormous debris fans. And if you look carefully in these rocks, you find zircons. Okay, so here's the original zircon that crystallized from a Bushveld-like magma. And here's now that zircon that was perhaps slightly abraded or perhaps slightly dissolved during metamorphism. But in the process of metamorphism, what happened is that a new rim grew on that zircon, and that new rim now gives the age of the metamorphism naturally, because that's when it formed. Okay, so we have a rim that gives the age of the metamorphism, but of course the central part of that zircon is the original zircon, and it gives an age of when that first crystallized. So now we have a zircon with two different ages. Here's an example. The top panel is an optical image of a zircon. The middle panel is what's known as a cathodoluminescent image, and I'm not going to explain that, and that's not terribly important, but the point is, in that image you can actually see the zones. And the bottom image is a scanning electron microscope image of the zircon. As we can see in that image, in this SEM image, there are shallow pits, for example, right here and here and here. And these pits are made from the ion probe. In the video on zircons that you'll see this week, there's some explanation of the analysis, but we use the ion probe to get a uranium-lead radiometric date. So we'll end up with a date for zone 1, this zone right here. We'll end up with a date for zone 3, and we'll end up with a date for zone 4. As you can see, zone 2 is very, very thin, so it's below the spatial resolution of the analytical technique. And when we date these three zones, we find that the central part of the zircon has an age of 3.7 billion years, or 3,700 million years. Zone 3 has an age of 3.6 billion years, and zone 4 has an age of 2.4 billion years. So basically, this zircon has experienced at least 3 episodes of erosion, deposition in a sedimentary sequence, burial and metamorphism, and exhumation. At least 3 of those, a whole cycle, a whole mountain building cycle in essence, so it records that. But not only can we date individual zones in zircons, there are other things we can do. We can, for example, measure the oxygen isotope composition of individual zones. From the isotopic composition, the oxygen isotopic composition, we can tell whether or not the parent rock had experienced hydrothermal alteration. And if it had experienced hydrothermal alteration, that implies that there was an ocean on the surface of Earth. We can measure the titanium contents of the zircon zones. And from the titanium contents, we can deduce the temperature at which the zircons crystallized, and that tells us something about the nature of the source rock, whether it contained water or not. Again, whether or not that source rock formed in a terrestrial environment that contained water. We can measure other things, such as the trace element contents of the zones in the zircon, their rare earth contents, the yttrium contents. And again, these give us specific pieces of information about the nature of the source rocks and the nature of the crust that the zircon was crystallizing from. We can even make more obscure measurements, such as the hafnium isotopic composition of the zircon. And this will tell us something about the source rocks. In particular, it tells us the time at which the source rocks that partially melted to produce the magma that produced the zircon. It can tell us the time at which those source rocks initially differentiated. So those are some of the things that zircons tell us. And so the point I want to make here then, in summary, is that the utility of zircons lies in the fact that they're hard, they're relatively unreactive, they can be dated, and they hold subtle geochemical clues that tell us something about conditions in the early Earth. And as far as some of the things that they actually do tell us, the oldest zircons suggest that a continental crust, a hydrosphere, that is to say an ocean, and a sedimentary cycle existed on Earth as far back as 4.4 billion years ago. They also suggest that the Earth differentiated, that is to say the bulk Earth differentiated into a mantle and a core very early on, within a few tens of millions of years of the assembly, of the initial assembly of the Earth from smaller planetesimals. There's one final point that I want to make here, and this is relevant because this is mainly for educators. This story about zircons is a good example of the nature of geologic reasoning. In this case, where we have combined spatial and temporal and analytical data to produce a narrative of Earth history.